stand on the shoulders of great people. Gerhard Dangel made the first Exta, and Dave Galt and Tony Barry made the Sexta, the southern version of that. And to use the same wordplay, I refer to this one as the MidWexta, because I'm in Illinois in the American Midwest. So there's a stupid name for it. How about that? This won't take very long. To make this device, you use the same GPS and Arduino as I showed you just a second ago. Instead of a single LED, we're now going to daisy chain a bunch of 64 LED arrays and then an 8-digit numerical display. These are all daisy chained into one chain. And it uses the Arduino's hardware serial peripheral interface, the SPI bus. And so these 5 wires have to be daisy chained together. Simple to do. Here it is, basically. In my device here, I took the 5 wires are connected to various pins here. By the way, I didn't explain before that these wires that go from this little header to the Arduino header over here are from the GPS. These go to the Arduino serial input. But the outputs to these display devices come from other pins here. And what I've done is underneath this board is ran wires to this little socket over here so I could daisy chain or use a single piece of ribbon cable more handily. Anyway, here's everything. This connects to, I don't know which one goes first. Probably this one is first. And then this chain, this daisy, the output of this goes to another one, and then the output of that goes to another one, and then this digital display is at the very end. And what it does is quite simply, it shows the UTC. It shows how many satellites it's listening to. And then at the beginning of every second, it starts lighting one LED at a time. And what I do is I light up a total of 500 of these. There are actually 512 in this array, but I skip the last 12 so that each LED corresponds to a handy 2 milliseconds. So at the 0th millisecond, it'll start and then go here, and then the next row, then the next row, all the way up to the top row. And from this, of course, you can tell is my camera and VTI time accurate? Is the shutter duration what I think, what it's supposed to be, what the camera is telling me it is? Is the VTI time that's being read out, does it correspond to this time? This all happens in the optical domain before any of these possible errors are entered into it. And again, as before, you use your IDE. The code for this particular thing is in this text file. You copy that text, paste it into the IDE. When you load it, be sure to throw that switch on the USB port to the direct position. After you finish loading it, change it back to the software serial position. Once it's back there, it's running. And you just record this matrix and the display, via your camera, your VTI, and step through the frames and fields to observe whether the times and output delays are accurate and what they're supposed to be. There are many characteristics that you can use with these. This one isn't as sophisticated as the models that the fellow Dave made in Australia, because it only works at one speed, one duration. The other things, if you want to change any of the settings, you can do it in the software code. So I didn't put any switches or make the ability to run slower or faster or anything like that. But it's very accurate. Here I have, I'm using a PC64 to record what's being displayed here. At the bottom, obviously, is the VTI, IOTA VTI output. And you can see that it corresponds exactly with what's being displayed on these numerical digits and on this matrix. These are 2 fields of the same video frame. You can see that the field is 16.6 milliseconds long, 2 fields, make a 30th of a second. For example, here, one field in NTSC is 0.01667 seconds, and you can see here that it corresponds very precisely to this value. 8.3 LEDs will be lit up for one field, and that's what shows here. Here's the next field, 8 LEDs further down the road. Here it is toward the end of a second. So we've just finished this row, row rather, and we're on the top row. And this will advance all the way up to the 500th LED, which is this one where my pointer is. And you can see this is getting to a high up in the seconds, milliseconds. Now, where chart finishes the 500 count, it starts again at 0, of course. And you have to be careful what you're reading here. There is no 90 seconds reading in time units. And that's what's really happening here is that 49 is overriding 50. Oh, what did I just do? Sorry. Oh, I'm lost. Yeah, okay, here's where I was. So here we are in the 49th second. But here, when it crosses over to 50 seconds, these the numbers here are going to overlap because it spent this half of a field in the 49th second, and the next half of the field is in the 50th second. So these numbers override each other. But over here, when it's the field is fully in the next second, you can see that the numbers are clear. And then it simply continues. Next to this device, you can see this is just my displays are in a cigar box here. Next to the cigar box is my little LED flasher that I just talked about, showing how accurate it is. Here at the beginning of this second, we're 2.2 milliseconds into the next second. And this first LED is just started to light up, and this LED flasher had just started to light up. Here we're fully into the second, and this LED is now fully illuminated. So here we have 3 GPS receivers. This is the IOTA VTI. This is that little flasher we just talked about, and this is the GPS receiver that's powering this display now. And they all correspond precisely with each other. Here's John Moore's version of this. He made, again, a nice 3D printed frame for his and put the displays behind that. And it's very nicely done. And that's it. I'm sort of done with this. I've used up pretty much all my time. I do want to show you some other gadgets for just a second. This will only take a couple of seconds. All of these are described in the Arduino timers directory that's in the IOTA group file section. This is a UT and sidereal time display. That's very precise. This was a real tour de force. This is accurate to milliseconds, and it'll be as accurate 100 years from now as it is today. A guy wrote me and said that he made one of these and put it in this lovely wooden box. I think he did a real nice job. The reason the display is so tall is because he also has longitude, latitude, and altitude showing up here. I didn't want to show you the numbers because it shows his longitude and latitude, and I didn't want anybody to go to his house and steal his stuff. Here's another device. This is my WWVB emulator. This is one of these little Arduino Nanos, the small version of the Arduino, and one of these little breakout boards. Okay, same functionality as the full-size board and shield. But what this does is it produces a 60 kilohertz RF signal. And when you put this little antenna, this is a couple feet long, next to an atomic clock, it'll set that clock. And you can use it to set an atomic clock to a different time zone. You can use it to set your atomic clock to UTC if you want to. Or you can use it to buy an American atomic clock and use it elsewhere in the world where WWVB doesn't even carry. So I took one of these down to New Zealand last year when we were still allowed to go to New Zealand, and had it running there, and I could show the local time, even though WWVB was, you know, tens of thousands of miles away, and it worked great. I think that's it, Roger. That's all I got.
Well, thank you very much, Art. That's very stimulating, and makes me want to go out and get one of those GPS timers so I can flash a non-video camera, digital camera, other than the QHY. Some of these cameras record at more than 300 frames per second, and you can flash them with that timer and get an accurate time on those flashes.
Well, you can do more than that. Let me just answer quickly. A lot of those timers have what's called a strobe output pin.
Mm-hmm.
The strobe output, if you use that to trigger an interrupt on the Arduino, can tell you exactly what the UTC time is at the instant of that strobe.
Mm-hmm.
So if you're clever enough, you can get that time and read it into a file and then know exactly when that image started. So,
sounds good. These are things worthy of study, and we'll see how we can develop them. Richard Nugent is next.